All right, welcome to this explainer on a really cool puzzle from computer science, matrix chain multiplication. Now, this is one of those classic problems that shows you how something as simple as where you put the parentheses can be the difference between a calculation that's over in a flash and one that could literally take centuries. So let's dive right in. I know, it sounds a little weird, right? I mean, we all learned in math class that when you're just multiplying, the order doesn't really matter. The final number is the same. So how on earth could just moving some parentheses around save you millions of steps? And there's the catch. You're right. The parentheses themselves don't magically change the math. The final matrix you get at the end is going to be exactly the same. But the amount of work, the sheer number of calculations your computer has to grind through to get there, oh, that can change a lot. We're not changing the result, we're changing the cost. Okay, so let's actually put a name to this thing. This challenge we're tackling is all about finding the optimal parenthesization. It's a fancy way of saying we're on a hunt for the single most efficient way to multiply a whole bunch of matrices together. So, what are we really trying to do here? Well, the goal is pretty straightforward. You've got a chain of matrices, and you need to figure out the best order to multiply them in. And best, in this case, means the order that uses the fewest scalar multiplications. That's just the basic multiplication of the individual numbers inside the matrices. It's a classic optimization problem. Okay, and this right here, this is the whole key to the puzzle. To multiply an A by B matrix with a B by C matrix, the total number of little multiplications you have to do is A times B times C. This one little formula is the entire reason the order matters so much. And boom, here's where it all clicks. Just look at these numbers. If we do A1 times A2 first, then multiply that result by A3, it costs us 18,000 operations. But if we do it the other way, A2 times A3 first, and then multiply A1 by that result, the cost skyrockets to 32,000. It's the exact same matrices, the exact same final answer, but it's nearly double the work. Wild, right? Okay, so we've got the problem down. Now, the most obvious solution, the one that probably pops into your head first, is, hey, why don't we just try every single possibility and pick the cheapest one? Well, that seemingly simple idea leads us straight into a massive trap.
This is what we call the brute force approach. You just try everything. And, it's tempting because it feels so simple to think about. But as you're about to see, for anything but the tiniest canes of matrices, this is a complete computational dead end.
And the reason this is such a bad idea has a very specific mathematical name: Catalan numbers. These are a sequence of numbers that pop up in all sorts of weird places in math. And the only thing you really need to know about them for our purposes is that they grow fast. Like unbelievably fast. Just look at this chart. I mean, it tells the whole story, doesn't it? That red bar, the brute force approach, it just goes straight up into the stratosphere. It's an exponential curve. Meanwhile, the blue bar, the dynamic programming approach we're about to get into, it grows way, way slower. The difference is just staggering. And just to really, really drive this home, if you have a chain of just 20 matrices, there are over 1 trillion different ways to arrange the parentheses. 1 trillion. No computer is going to check all of those in any reasonable amount of time. So yeah, brute force is definitely out. So if brute force is the villain of our story, then dynamic programming is the hero. It is an absolutely beautiful and elegant technique for solving problems that happen to have a very specific, very useful kind of structure. And it turns out this problem is a perfect candidate for dynamic programming because it has 2 key properties. First, optimal substructure. This just means that the best way to solve the big problem, say multiplying matrices A1 through A6, has to include the best ways to solve the smaller pieces, like A1 through A3 and A4 through A6. The second is overlapping subproblems. This means that a dumb recursive approach would end up solving the exact same subproblems, like the cost of A2 times A3, over and over and over again. Dynamic programming is smart enough to solve it once and save the answer. I absolutely love this analogy. Think about building a piece of IKEA furniture. You don't just start nailing random boards together, right? No, you build the drawers perfectly first, then you build the main frame perfectly. You make each little subpart as good as it can be so that when you put them all together at the end, the whole thing works. That is the essence of optimal substructure. Okay, don't let this formula scare you. I know it looks intense, but the idea behind it is actually pretty straightforward. All it's saying is this: the minimum cost to multiply a chain of matrices from some matrix I to another matrix J, Well, we can find that by trying out every possible place to put the final split, which we'll call k. For each split, we just add up three things: the already calculated cost of the left half, the already calculated cost of the right half, and the cost of multiplying those two final chunks together. We just do that for every possible split k and take the one that gives us the minimum total. That's it.
All right, theory's great, but let's see how this actually works in practice. The algorithm is what we call bottom-up. It solves all the tiny, easy problems first, and then uses those answers to build up solutions to bigger and bigger problems.
We start by setting up a table. We can call it M, where we're going to store all our costs. Now, the cost of multiplying just a single matrix by itself is obviously 0, right? So we go ahead and fill the main diagonal of the table with zeros. We'll just imagine everything else is set to infinity for now. And the process is super systematic. We're going to fill this table out one diagonal at a time, moving away from the center. First, we'll calculate the cost for all the chains of length 2. Then we'll do all the chains of length 3, and so on. And the cool part is, each new diagonal we fill in uses the answers we already found in the diagonals before it. So, after our first pass, the table starts to look like this. We've gone through and calculated the simple costs for multiplying A1 times A2, A2 times A3, A3 times A4, and all the other pairs. These are our smallest, simplest subproblems, and now their answers are locked in. And after we just keep repeating that process, filming the table out, diagonal by diagonal, building on our previous work, eventually we're done. The whole table is full. And the answer we've been searching for this whole time, the absolute minimum cost to multiply the entire chain, is just sitting right there in the top right corner. All that work building up to one single optimal number. Okay, so we've found the answer, we've filled out the table, but so what? What are the big takeaways here? Why is this considered such a cornerstone problem when you're learning about algorithms? Well, for starters, the efficiency is a game changer. This dynamic programming solution runs in what we call n-cubed time. The space it needs is n squared to hold onto those tables. Now, that might sound like a lot, but compared to the exponential time of the brute force method, this is predictable, manageable, and just worlds better. And hey, if you're ever prepping for a technical interview, this is basically your cheat sheet. You gotta know the complexities. N-cubed time, n-squared space. Super important is knowing why simple greedy ideas don't work, like just always multiplying the cheapest pair first. It's because this problem has that optimal substructure we talked about. And one final crucial detail, that table we built tells us what the best cost is, but to know how to actually get it, we need a second table that remembers where we made the best split at each step. That's how you reconstruct the final parentheses. And that really brings us to the final thought, this whole bottom-up philosophy of meticulously solving all the small, easy subproblems first so you can build your way up to the solution for the really big problem. That's the soul of dynamic programming. And you see this powerful idea everywhere, from aligning DNA sequences in biology to optimizing queries in huge databases. So the real question to leave you with is, where in your own life or work could you solve a big, messy problem by just solving all the little ones first? Thanks for watching.